For the TriColumn design and also for your assignments later on, you will use this book. It's called Sinot, Colson and Richardson, Chemical Engineering, third edition. I don't know if you have the newer edition of this one. That's also okay. And in this book, in a chapter in the volume 6 for chemical engineering design, we what will I explain here is based on the chapter 11. So it is like really about handbook, yeah, of the Richardson, Colson and Richardson. We use a lot in chemical engineering, and then for this one is for chemical engineering design, volume 6. And we'll go to a little bit long. Oh yeah, sorry. Oops. Yeah, chapter 11. Costing, material, design. There, yeah. So, um, all about the separation column in distillation, absorption, and extraction. We're gonna learn about here. Here, and then there's also a multi-component distillation, and then this one is the plate hydraulic design and how to design the column sizing. We're gonna use this one, yeah. Okay. Right. Okay, so I'm gonna explain it first from the first PDF that put into the EduNext about the tricolumn. Mm, right, but I have a problem here because I can't write anything. Yeah. Okay, I'll just explain it. Okay, so as we know, the tricolumn. Um, as we know, the tricolumn is to one tray. It's actually it actually say to like one equilibrium stage. Okay, so um, so right, can you maybe close? Okay, right. Okay, so in tricolumn, they want to put they want to make an equilibrium by adding the liquid inside the vapor from the tray below, and then contact with the liquid from the top. Maybe Dama can. Okay, maybe you want to. Okay, you want to mute it first. Right. Okay, okay, so we know that one stage equilibrium is actually we have a liquid flowing from the upper tray and also vapor coming from uh, the lower tray there, and they're just gonna mix them together and then until up to the equilibrium if the efficiency is 100%, and after that, after 100%, then they're gonna leave with the uh, new composition, yeah, with the new composition. This is the new vapor, and then this is the new liquid phase. Okay, so the function actually the contact or the contact between the liquid from the top and also the vapor from the bottom is actually can be done in a tray column or in a pack column, column packing atau kolom baki, ya, tray. But for our understanding and in our study here, we're gonna use tricolumn as an example for distillation. Okay, so yeah, so the function of tray is first to mencampur uap dari bawah, ya, so to mix the vapor from the bottom part, from the tray below there, that raise up and then contact with the liquid, and then it will go to the equilibrium position, ya, menuju komposisi keseimbangan uap cair. So once it goes into the equilibrium, then it will leave out. They should also leave out with the new composition both of the vapor and also the liquid. Jadi harus bisa memisahkan campuran uap cair. Okay, so what is the our column design, rancangan kolom? In our what we're gonna do in the column design, so we will also know we're gonna train, or we're gonna have a practice to determine the column diameter. How big is the diameter of the column, or how small of the diameter of the column, and then the space between the tray spacing. The tray, for example, there are 30 centimeters, there are 60 centimeters, there are 90 centimeters, or sometimes there are 75 centimeters for the basic, yeah. And also the tray configuration. Okay, so there's a number of tray configuration to make sure that the liquid can flow from the top to the bottom, and then the vapor can also raise up from the boiler there, from down there, and then raise up to the front. Okay, right. Let's have a look. Okay, so this is the. Okay, let's make it bigger there. Yeah. Okay, so this is the what we see in the TriColumn. So basically this one is one tray where we have the liquid in, and in order the liquid to really have a contact with the vapor from the bottom, there would be some sort of a hold like a baffle, yeah, ada pembatas there. So the liquid will have a hold up over here, and then it will flow to there. Okay, right? And then from the bottom there a vapor. So the vapor will go up, and then it's actually here there is a hole or a sieve tray, kayak penyaring ya, look like a sieve tray, seperti penyaring. Or if you have a steamer at home, yeah, in bahasa Sunda is called langseng. I don't know in bahasa Indonesia ya. Steamer, pengukus ya, pengukus. So you have some sort of tray, and then with a lot of hole in it, so the vapor can rise up there, and while the vapor is rise up there, it has a contact with the liquid. Yeah. So if we think that one stage equilibrium is where the liquid meet the vapor here, so we suppose that the equilibrium will or the mass transfer between the liquid and also the vapor will be carried out here, and then we need to put some time, yeah, on here, like a residence time, and after that it will leave out a new equilibrium, so where the liquid with the new equilibrium composition will go down there in the downpour there, and also then the new vapor composition is leaving this tray, yeah, with the new vapor composition. Okay, and then we have the gas out, and then maybe we can this will be connected into the condenser, and then from condenser there would be like a holding tank, or a separator tank, and then from the separator tank of course that would be it should be divided, yeah, with the reflux ratio, some of them going inside and some of them is taken out as the distillate product. Okay, so then and then the liquid goes to the next tray, the tray number 2, and again it will follow the again the similar condition like this, and then again put it there, yeah. So and then they go here around there, and then in the end we have 1 2 3 4 something, yeah, or more than few trays. Okay, so this one is the phenomena inside the tray, if we can see it. we have vapors coming out and also the liquid flowing down there. Okay, now if we'll left out those liquids and vapor, and then we have a look at the sieve tray or the equipment itself. First we're gonna see a sieve tray, sieve ya, seperti steamer atau pengukus. So you can see this, there's a plate or a sieve with a number of hole there, and then here you can see here there is a joint between the cap and also the body. So the body looks like a pipe, yeah, like a large pipe there, and then here there is a hold up of the liquid, and then it will go there, and then it will go inside like that. Yeah, okay, so this is the and also here there is a cartridge support rod, so to support the tray, and then here is called downcomer or down spout or downcomer, and then there's a lip seal and also there's a liquid seal. Okay, so our job is to design all of that. Yeah, how many tray we need, how long is the trays, the space between the tray spacing, and then should we have the baffle or not, and then how big or small is the diameter. So we're gonna design that based on some problem specification. Right. Okay, so let's look at this type of the flow in the tray. Yes, skema aliran di tray. Okay, so if we sketch, this is the tray for one tray. Okay, and then this we have a plate above here. Then we know that around this area the plate has a hole, like a sieve, right? And then in this part is the there is a liquid from the top, and then it will have a hold up around here in the wear there, and then of course the clear liquid will have a froth seperti busa-busa ya, like a froth in your coffee. If you have a latte or yeah, cappuccino latte or something like that, yeah, and then you have a froth busa di atasnya. Okay, so the contact between the vapor and also the liquid will cause a froth, berbusa-busa, yeah. So if you think about the bubbles or busa, yeah, busa-busa, that one there, it is actually some sort of not emotion, yeah, just the a contact between the liquid and also the vapor there. Okay, so this is the liquid will fall, and then they're gonna mix them together with the vapor. So the froth means that the vapor is trapped inside the liquid, but on the top of that there's also spray. Spray means a droplet of liquid that hanging around on the gas, okay, or in the vapor. Okay, and then it just gonna go in this area in the calming zone there, and then and down come around, and then there it goes again, the next one. Okay, so if you think this one is full of the liquid, this one is full for the liquid, so it is the active area where the equilibrium is happening. Okay, so this is the active area where the equilibrium or the contact between the vapor and also the liquid is happening, and yeah, we should calculate it based on this side. Right, I'm just gonna stop here, and then do you have any question? Okay, let's go through, yeah. Okay, so for the flow pattern aliran arah cair on the tray, we have a single path. We have a single path on, that means it looks like this, yeah. So this is a single path. So we have the liquid coming from the top we have the liquid coming from the top here. Yeah, oops. We have the liquid coming from the top around here, and then it will go that way. Okay, and it will go that way, and it will leave into the next small around here, yeah, small canal around here, just so it will go that one. So this is called a single path flow. Okay, the second one is called the reverse flow, where the plate has a border, pembatas, and then the liquid goes that one there, and then it will travels to the some of this, and then put it back there. Okay, of course it's gonna change a lot how about the design. Okay, and then the third one is the multipath flow. So it's actually for even for one flow there are two paths, yeah, from the center there going to the near of the on the corner of the diameter there, and on this one also going that way. Okay, so the multipath flow. But usually for the design, for the diamond, we usually use the single path flow. For the single path flow or reverse flow or multiple flow, so all of them have different configuration and also different calculation. Right, and then let's have a look on the type of the tray. Okay, the type of the tray, we have an example. If the first one is the one that we often use is a sieve tray or perforated tray, jadi bolong-bolong, yeah. In the sieve tray or perforated tray, it looks like a plate, and then with a lot of holes on it, and then the hole is also have a pattern. A sieve tray is the I think the cheapest one among bubble cap and also false tray, but of course in the sieve tray we have of course there are the good things, yeah, and but also it has a there's a benefit of that one because it's cheap, and it is simple, it is easy to calculate. But the drawback of sieve and perforated tray is you're prone to have maybe a drop, dripping, yeah, if you have too much liquid, or maybe easy to maybe that one there, maybe sometimes it's not effective enough to hold the contact between the liquid and also the vapor. So because it is only perforated, hanya bolong-bolong, yeah, so maybe there's some chance that the vapor just go out, yeah, before it have a contact with the liquid. So then the mixing and also the equilibrium is not 100%. Okay, the second one is the bubble cap. Yeah, in a bubble cap, we have a cap. We have a so we have a like a small like a small hole here, and then it is put with a cap, ya, gitu, kasih tutup. Okay, so apparently the vapor should go that way and then go down here, and then before it leaves the cap. So the time contact between the vapor and the liquid is much better than the perforated tray or the sieve tray. Okay, and then even in the fender, there is a number of types of the cap. Yeah, this side, that side, yeah, and then they will go. This is also perforated, bolong-bolong, yeah. So the vapor goes that one there, whilst it is still in the liquid. So they have a good contact with the liquid. Okay, but of course the drawback of a bubble cap is more expensive than the perforated tray. Okay, and the last one is the this one is called the tray, the valve tray. In the valve tray, the valve can go up and go down, so it's gonna close if there is no vapor, yeah, but when you have enough pressure of the vapor from down there, the valve will apa, naik ke atas ya, but they will push the valve tray and also go that way, and then it will mix with the liquid. So still it has a good contact with the liquid, but also if there is no much gas coming out, it will close down, so the liquid won't have a dripping, jadi liquidnya nggak akan bocor gitu ya. But the drawback of the valve tray is they will require quite pressure from the bottom, so it will leave quite a good pressure drop. So we have to compensate those pressure drop. This is an example of valve like this. Okay, so this is an example. Okay, so this is a contact, yeah, illustration of liquid vapor contact in a tray. This is for bubble cap. So if, for example, this is the liquid, so you have the vapor rise up there, and then first it will go to the inside of the bubble cap, and then leaving out in those holes around here before it rise up. So if you think oops. Okay, so if you think here that the bubbles, which is have a composition of the vapor here, will have quite time to have a contact with the liquid. So hopefully the contact become much better, and the equilibrium is happening, and also the new vapor will leave with the new composition. Okay, the next one, okay, this one is the example of perforated tray or the sieve tray. So if you think about it, this one here, the liquid, sorry, the vapor will go just straight, have a bubbles here, and then they will pass those liquids there and then just go up. So if we don't design it nicely, then sometimes the liquid will the vapor will just go up before it has a good contact with the liquid, or the liquid will just pass that one, yeah, before it have a contact with the vapor, and then so the efficiency is not as high as the bubble cap. Okay, and the other way around, if you have not much liquid, if you don't have much gas flow, then because it's only there's a hole here, of course the liquid will have a dripping over here, ya, akan jatuh ke bawah. Okay, then of course we don't want the liquid with this composition leave the tray with the similar composition with this one, because of course we want the liquid to have a different composition with the new equilibrium composition that leaving the tray. Okay, so anyway, it is quite complex when you look at the fluid dynamics of it or the fluid mechanics of it, yeah. Okay, this one is also the second one is also a flow pattern of the bubble cap there, yeah, from here and then to there. Okay, so sometimes this also a complication in a sieve tray or in the perforated tray, that if you have too much gas, if you have too much gas or too much vapor, then it will just go straight. So the composition of the vapor here just go straight that one there with the composition of the vapor in the bottom, while ideally it should be contact with the liquid first, and then we'll leave out with the new composition. Okay, This one is the valve tray. A type of the valve tray. There's the one that rise up, yeah, with the here, and also around here. This also, yeah, this is a type of the valve tray. And we know also with the valve tray you have more time to have a contact with the liquid. But the drawback is maybe this one is more expensive than the others. Okay, so let's have a look about the tray and the column. Usually we have to design the diameter of the column, and then in here there is a downcomer and the wear, penahan ya, penahan liquid. And then this one we install it in like a tile ya, kayak lantai. And then if sometimes the distillation column is large enough, so sometimes there are with the 3 meters in diameter, maybe 5 meters in diameters, so it has a manway. Manway is the one that we can open it, and then the man or the operator or the cleaning can go inside here and then to clean, and then to yeah, and then maybe to change the tray with the new one. Okay, and then here we have the calming area from the top, and also there is a support ring. Here there is a penahan ya, a demeanor beam support clamp with support angle ring, and also the peripheral ring clamps. Okay, so if we have a large diameter, sometimes up to 5 meter, or maybe sometimes 6 meters, with the height of it can be up to 50 meters, and also sometimes it can be up to 9 maybe 60 meters ya, 60 meter tingginya ya. So it's a very tall. So if you have a kunjungan pabrik, yeah, you will see that in Pertamina, for example, or in a chemical, if you have something towers, if you have a lot of towers with the high tower, it is actually yeah, it may be a distillation column or absorption column. And there's also the ratio, you have to check it with the book, but the ratio between the diameter and also the height is around 10, yeah. So if you have diameter is 1 meter, so the height should be 10 8 to 10 meters, yeah. So when we design, we have to think also the aesthetically, yeah, we have to think about the aesthetics of the tray. So don't draw or don't design the tray that is maybe a fat and short, yeah, short. For example, okay, Bu, this is my design with the diameter of 3 meter and also the height of 6 meters. Okay, even it satisfy all of the design, because we don't want to make a separator, yeah? We want to make distillation column. So the distillation column should have a tall appearance, and then so then it is better if you change again your calculation and then do revision. Okay, so that's why in this case TriColumn design is an iterative process. You can do it 2 times, 3 times, or even 4 times if it is satisfy all of your criteria, but on the ratio of the diameter and the height is not complied. Okay, all right. Let me stop it here. Do you have any questions or comments about? Oops, sorry.
Miss,
Yeah, yeah.
the aesthetic part where the ratio is 1 to 10, is it like an actual standard, or is it just a rule of thumb?
Um, there is a rule of thumb in the book, in the CNOT book. I think around yeah, uh one 8 to 1, yeah, 8 for the height between 8 to 10, or I don't know. But when you do the assignments, check again in the C notebook about the L over D ratio. Yeah, L per D, length per diameter. There should be some comments on that. I have an interesting experience. Yeah, a few years ago, I taught the master students at process engineering, yeah, on a Saturday. So the process engineering is a type of master in chemical engineering ITB that they actually the one who do the study is actually a process engineer, jadi pekerja gitu ya, because of the process engineer, so they study only on Saturday. Okay, so and at that time I taught them about distillation column and also the using of HIFIs. Okay, and I show one of my students work, yeah, about the packing column design at the moment at the time, and then I talked about that, and then I showed it to them, and then they talked to me then, Bu, ya bagus sih, but itu terlalu buntet. They said, well, what is buntet? Terlalu gendut ya. It's like too round gitu. It's not very tall. So actually, even yeah, in the plan itself, um, when we want to uh, accept the design, there's some certain rules. Okay, I forgot the pages, but if you look at the um, this one here, so maybe let's check the 556 556 maybe. Okay, yeah, so this one is so this is an example of the TriColumn. Yeah, so yeah, this one there. I think look at around this chapter here. There should be some an example, yeah, or the rule of thumb to get those L over D. I think around 8 or 10. Okay, right. Okay, any other questions? Oops. Right. Okay, so let's have a look on the comparisons, perbandingan between the trays. Okay, so for the type, the sieve tray can holding up a very high capacity, and false tray is high to very high. A bubble cap is moderately high, and for dual foil can accommodate a very high capacity. Sieve tray has a high capacity, and then for the turn down is 2/1, and then the entrainment is a moderate, both of them, and then the pressure drop, it is quite low to moderate, but for bubble cap uh, it has a high pressure drop because the vapor should goes inside those cap first, yeah, because it's travel. And then the cost, the sieve tray or dual foil tray is very low because it's much simpler, and the false tray is higher than the sieve tray, and also the highest one is the bubble cap. And then but the sieve tray have a good low maintenance. Low maintenance is very important when we operate them, and then we do it for very long time, yeah, 10 years, 20 years. So of course there is maintenance is a very difficult one. Okay, and then a bubble cap has a relatively high, so then if you have for example after few years, then you have a corroded bubble cap, and then so we have to contact with the vendor and then buy the new one and then install it again. Of course it will used to have a down the turn down, or there is no operation at that time, yeah. And then also the falling tendency, also this is one is low, but in the bubble cap it has a high, and then it tend to collect solid if there is a solid inside those liquid there. And then the flow cannot yeah, it's very low and then suitable for solid handling. Okay, and then for the corrosion, the bubble cap also is prone to corrosion. Yeah, so okay, so this one here, so at the moment about valve tray is about 70%, and the share of market sieve tray is 25%, and then it is main application for low flow condition and where the leaking in the liquid, yeah, should be minimized. Right, okay, so now let's have a look on the operation area for the sieve tray, which has a stable area. Okay, right. Uh, so in the satisfactory area should have a range of the vapor and also the liquid rate. Okay, so what happens if the vapor is too low and the liquid flow rate is too high? Okay, so that would be weeping or dripping, menetes ya, menetes ke bawah, liquid menetes ke bawah, so it's gonna be weeping. Okay, so and then this is the dash line is called the weep point, and the lower one is the dump point. Looks like the if the vapor is very slow, of course the liquid will just flow around those sieve tray ya, akan menetes ke bawah ya. Okay, we have to of course we don't want to have this one is to happen, so we have to avoid this weep point. So later in the design there's a criteria to check if the tray is weeping or not. If the tray is weeping, then we have to check again to do the new iteration with some other condition. Sometimes we change the diameter, sometimes we change the flow, or some ideas. Okay, now if we have a too much vapor, yeah, with the low liquid rate, this one, it is called entrainment. What is entrainment? Entrainment is called carryover, where the liquid from the down from the tray on the bottom on the lower part is carried over to the tray on the top one, ya, yang di atasnya. So it bring the liquid that one there to the upper tray. Okay, so we don't want that, so we don't want entrainment, so it's called the excessive entrainment if we have too much vapor flow rate and low liquid rate. Okay, akan ikut ke bawah ke atas ya, entrainment. Okay, and then if we have high vapor but also high liquid rate there, very high vapor and also quite a large liquid rate, what happens is we have an entrainment flooding, or it goes carried over, akan ke bawah ke atas, akan banjir tapi ke bawah ke atas ya. So the liquid will go up there and terbawa ke atas. Of course, we don't want the entrainment flooding, so the excessive entrainment and also the entrainment flooding will be the border, yeah, border of our design, because we don't want this happen. And then if we have too much liquid and also the vapor flow rate is not as high, yeah, like that, that like this one here, so we will have a downcomer flooding, which is the liquid will just flowing up without it have a contact with the vapor. Okay, so we also don't want the downcomer flooding, so maybe we have to change the uh, the the liquid, or maybe increase the wear ya. Wear tuh kayak penahan ya, penahannya, or something like that. Okay, Okay. So, what is flooding? Maybe I have to go back there to the schematic. Okay, yeah. So here the entrainment carried over is actually when you have a drop of you have the drop of liquid there is carried over to that one. So it's called entrainment, carried over, kebawa ke atas. Okay, sorry. Okay, and the next one, if you have excessive flooding, then it's actually you have a lot of liquid there, and then not enough vapor, so it goes that way, and then it'll just go right into the next one. So it's gonna carried over there, akan banjir, flooding, without the liquid will have a flooding without it have a contact with the vapor, so it will have a similar composition with that one there. Okay, and then what else? Yeah, and also the entrainments. Yeah. Okay, so sometimes the L over V ratio is also have a influence, yeah, with the downcomer flooding. Is it downcomer flooding, or is it entrainment ke bawah ke atas, or spray entrainment ke bawah ke atas, yeah. So if had have a low pressure, and then you have a low L over V ratio, maybe here, yeah, with the small pressure, so maybe you have a spray entrainment. If you have quite entrainment downcomer flooding around this area, and if you have enough pressure, sometimes it will have a downcomer flooding. So later on in the TriColumn design, what you need to do is to check all the criteria that we have to fulfill, and then we need to check the calculation, if our calculation satisfy those criteria or not. If it doesn't comply to those criteria, then maybe we have to change some of the parameters. We have a lot of parameters that need to be changed. That's why it's called the design. So the term of the designs means you have a lot of parameters that you want to check, yeah. You want to check, you can change, you can design by yourself, you can argue, you can check that one. Okay, so yeah, it is would be based on your assignment. All right, right, I think let me check. Okay, I think we can continue tomorrow. So for tomorrow, I will try to explain about the column design, or maybe just few more slides here, ya. So sometimes we have a different vapor and liquid. Laju uap dan laju cairan bagian atas dan bagian bawah berbeda. Okay, so sometimes we have a different column for the top one, and also the bottom it can change. Yeah, I remember if we have, for example, 70% of methane, and the remaining is just C2C4, C5, for example, we have a very big top, big diameter on the top and lower diameter on the bottom. We can have a different column, ya. Kita bisa punya dimensi kolom yang berbeda bagian atas dan bagian bawah. So the tray column design on the top, ya, the rancangan kolom bagian atas is actually going to be represented by the top tray. So we have to check the composition and also the properties of the top tray of the column, and then we will use those as the design. And for the bottom tray, rancangan kolom terbawah diwakili oleh tray terbawah dalam kolom. or the column design of the bottom one, it will be represented by the lower tray of the bottom, because maybe the specific gravity, the all the properties will have different properties. So sometimes we need to calculate the top one and also the bottom one. Okay, so maybe in summary later on, we need to we need to make this one first. So we have to check the molar rate of the vapor, and also the liquid, also of course the temperature, and then the molecular weight, and it gonna lead with the how many is the density, and also the mass flow, and also the volumetric flow, and also of course the surface tension also is gonna use. Okay, right. Looks like I think I should just stop it for now. Tomorrow, if you can have a look, checking this PDF, that would be very good. Tomorrow we'll have start to have a discussion, and then also designing the tray column with the sieve tray, and I really want you to listen it carefully tomorrow, because this gonna be all the algorithm that we gonna learn is gonna be based for the tray column design. All right. Any more questions? So, and okay, so this one, you may want to check the Synod and Colson and Richardson. Maybe you can ask your friends if you don't have any, and then the pictures also is from Kister distillation operation. If you have that one, you can also yeah, this would be useful too. All right, looks like you also have another class to go, so that's fine. So let's stop the recording.